Marco Miniaci, as our second webinar speaker. Marco is a specialist of seismic and mechanical metamaterials, and today we'll talk about inspired elastic metamaterials. So Marco, it's all yours.
Okay, so first of all, thanks a lot for the introduction. I would like also to thank the organizers for having invited me to deliver this talk. I think that organizing this kind of very exciting series of webinar in this specific moment in which metamaterials field is kind of exploding could be very interesting. I hear some noise. No, there is Jonas that has raised a hand. Oh, okay. Shall I continue?
Sorry, so Jonas, you are raising your.
Yes, please do.
Okay, that's fine.
Okay.
Please stop pushing. Okay, go ahead.
Sorry. So, well, I was telling that having this series of webinars in this moment in which the field is kind of exploding, I think that is a very good idea. I still have somebody raising hand on my screen. Maybe somebody want to ask some questions?
It's Younes.
Okay.
Younes, do you have any question?
Marco, I suggest that you go ahead for a good 10 minutes before answering any questions, okay?
Okay, cool. So, thanks again for inviting me. And let's say, my name is Marco Miniaci, and now I am a researcher at the CNRS of Lille, at the Institute of Electronics, Microelectronics, and Nanotechnology. As first thing, I would just to share with you the outline of the present presentation. As a general statement, we can say that I will start from, let's say, the context and the motivations that push the works that I will be talking about. The context, of course, we talk about some bio-inspired themes that we were examining with my colleagues in the research in the recent times. Then I will talk about some, let's say, the introduction of hierarchy in elastic metamaterials. Do you see the pointer of my mouse?
Yes, we do.
Okay, cool. Then I will talk about the concept of tacticity in elastic metamaterials and try to explain how also this concept is kind of related to the bioinspiration. And then the third topic, I hope to have the time to do that, is to see how it is possible to design photoresponsive tunable elastic metamaterials. Then I will go rapidly towards conclusions and the acknowledgements. I would say that this, the motivation, the context of this research was born for the first time when I met Nicola and Federico, which basically is the research group where I did my first postdoc. At that time, I had my PhD was on metamaterials, and they were specialized as a group specialized in bio-inspired materials. And so I came across, let's say, the need of researchers and scientists to find solution into specific technical challenges, such as, for example, architecture, aerodynamics, mechanical engineering, material science, and so on. And during, let's say, this meeting, I came across with the idea that biological structures indeed represented a constant source of inspiration to solve this kind of problems. For example, here we can see the very famous Leonardo da Vinci flying machine, which is known to everybody. That was a kind of inspiration that Leonardo was trying to find from nature to fly. In this kind of approach, I would like also to point out the difference between biomimicry and bioinspiration. So in the case of the Leonardo da Vinci flying machine, it was more biomimicry, because Leonardo was kind of looking at the animals and trying to reproduce exactly the same mechanism to obtain the same functionality. On the other hand, in a more, let's say, general and broad sense, we can talk about bioinspiration, which is a little bit less strong. And so, for example, we can imagine that bioinspiration is to, in general, is to study and draw analogies from biological systems to engineer advanced materials with unique dynamic properties. So here I just would like to bring to your attention some of these examples. For example, in 1941, George de Mestral pulled some Badrox bars from his dog after a walk in the countryside. And let's say, pushed from scientific curiosity, it observed this material to the microscopy. And actually, he discovered that this kind of biological systems, they have a specific structure. Here we can see some images that have a kind of a hook shape. And of course, this was responsible for the sticking mechanism of the animal fur or whatever. And so a few years later, if I'm not mistaken, in 1950, he patented the Velcro, which is a well-known nowadays way of, let's say, closing things. Here, I would like to bring your attention to, let's say, another examples. For example, the Shinkansen bullet train was one of the fastest train up to a few years ago. I think that it should still be one of the fastest. And it was able to travel at a very high speed, up to 200 miles per hour. However, it had an important issue. It was a technical issue that was coming from the fact that when he was entering and going out of galleries, he had he produced a kind of shock waves that produced some bumps that were that people even 1/4 of miles away were able to hear. And so, of course, the problem was the noise. So let's say the engineer that was responsible for this, Eiji Nakatsu, he started asking himself the question, how could I solve this noise problem? So he was asking himself if there is something in nature that travels quickly and smoothly between two different mediums. The answer, let's say, found in nature was the kingfisher. This kind of bird, it's able to move between two media with different densities, so like air and water, and the water splashed once that he tried to catch the fish is minimal. So basically the idea of the engineer was to be inspired by this biological system, by the bird, and produce the design of the train in a similar way. This produced a 15% less energy use, even if the train was traveling faster, 10% faster. Here there is, let's say, more less nice example from the design perspective, let's say, and it's a car, the design of which has been inspired by the boxfish. I would say, and I would guess, for like the idea was to maximize here the volume of available in the car. So let's now go rapidly through some examples in architecture and in sport. For example, on the top part of the slide here, we can see that we have the famous Beijing National Stadium, which is inspired by the bird's nest. And below here, we have shark skin inspired swimsuit, which actually, here it's a nice story, because actually researchers tried to study the shark skin, and then they realized that actually designing the swimsuit was behaving even more than the shark skin in the ocean. Well, let's say from a drug perspective. Of course, the shark skin may have even additional functionalities. The last example with which I would like to conclude, let's say, the introductive part, is the stomatopod dactyl club, which is known to be a formidable damage-tolerant biological hammer. And if we give a look also in this case more in details to the type of microscopic architecture of this structure, we can see that it is made, it is very complex, and it has some characteristics of being multi-phase, multi-scale, and have a hierarchical organization, and functional grading, optimized geometries, and all this. I would like to bring, let's say, our attention. Johannes has raised his hand again. Okay, I will continue. I would like to bring our attention on the hierarchical organization. This hierarchical organization, let's say, why I decided to focus on hierarchy, because there are a lot of natural materials, such as, for example, the nacre, or for the protection, or the resilience of wood, or even characteristics of light filtering, such as in diatoms, that indeed it has been proved that derive exactly from a material that has a structural organization at different length scales. So here we can see what has been done in statics, because let's say that from a static point of view, the role of hierarchy is rather investigated, rather known, and its advantages are already explored. And let's say that we could summarize in telling that hierarchical architecture in statics can achieve the goal of minimizing the material use while optimizing structural performance. So the question that we decided to ask ourselves was, what happens in dynamics? And specifically, what happens in metamaterial dynamics? So just a slide to briefly revise what is, let's say, what we mean for metamaterial, even because the terminology is getting quite confusing in nowadays. But let's say that we can more or less define metamaterials as to be considered as composites having a three-dimensional, periodic or not periodic, cellular architecture, which is designed to produce a typical dynamic response to a specific excitation. And here, for example, on the top right, we can see that there is, for example, the so-called bandgap performance, which means that in this frequency range, no vibration modes can be associated to this structure. In general, I would say that this kind of unconventional behavior could derive from periodicity of the system, which is referred to as Bragg scattering, and so generally people refer to this as phononic crystals, or to resonance of specific resonators that are embedded in the material. Let's say, from the point of view of hierarchy, we can see that recent studies have reported about hierarchical and fractal-like structures, which in general combined the property of wave filtering and additional functionalities, such as, for example, increased strength or increased thermal resistance, etc. here, for example, I report some, of course, all the bibliography that I report here is not exhaustive at all. I mean, it's only a few examples that I prepared just to make the talk. But, for example, some of these cases, we can see that reproducing the Necker-like geometry in which we have a biphase structure. So we have two materials, one that is very soft and another that is very tough. And this pattern is repeated at multiple scales. Or we can see that here we have some structures that are of lattice type. And for example, let's say that all these structures resulted in additional band gaps and controlling the wave directionality. But in these cases, we have, let's say, some limitation deriving, for example, from the fact that we have to put together two materials very different from one each other, or for example we have kind of lattice type structures. So our idea was to imagine to approach this problem from a different perspective, which is to have continuous structures, so monophase structure made of single materials, going in the direction of having lightweight structures, and this structure we would like to be the most simple possible to manufacture. And of course, one of the first idea that came to my mind was simply to drill holes in the structure. In this case, we went to let's say, take our bioinspiration from Coscinodiscus centralis biosilica valve, which is basically a kind of diatom unit cell, and exploring at, let's say, this very first stage of bioinspiration, exploring this type of geometries, we could see that two main design principles were used in nature. One, this one on the left, was that the hierarchical levels were at the same spatial scale. So here you can see that basically this and this unit cell, they lie more or less in the same spatial scale. And the second strategy was to use completely different scale level. So you can see that here, this unit cell is very small compared to the next hierarchical level. And this brings so to two different case studies that have, of course, different weight reduction, and that can be identified by the so-called hierarchical factor, which is the unit cell size of the hierarchical level n divided by the unit cell size of the next hierarchical level. In the first case, so this one, we can see that this number is close to 1. On the other hand, on the different hierarchical level, this number goes to 0. Concerning the calculation method, we used two, let's say, I would say, standard approaches. The first one was to have 2D, or I would say even 3D, we will see in some cases, wave equation with block expansion theorem. And of course, this plus the standard finite element discretization procedure will give rise to typical dispersion equation in which the stiffness and mass matrix are not frequency dependent. On the other hand, in some cases, we explored also the viscoelastic properties in which the problem starting having elastic problems that are frequency dependent, or the elastic modulus starting being frequency dependent. Concerning the type of viscoelastic model, we used a Kelvin-Voigt model in which, of course, we have only one viscosity parameters. Going to the results, we can see that in the first case, so when the structure has the hierarchical level is at the same scale level, we can see the following things. If we compare the dispersion diagrams here on the left for the non-hierarchical structure, so the ordinary structure, and the hierarchical structure, this one on the right, we can see that we have a partial conservation of band gaps, which is represented by this gray rectangle. And I say partial because basically what happens is that we can introduce some additional bands, for example, this one, or we can have the shift of this additional band towards lower frequencies. And this is due to the fact that introducing the hierarchy, we have introduced new degrees of freedom in the structure. Another thing that we can also observe is that that it's possible to introduce new hierarchical induced band gaps at mid frequencies, and here is the little red band gap here that was not present in the previous structure, and the dispersion curves are not altered at the low frequencies. Of course, here we have a stiffness mass alteration. Bogdan is requesting to annotate the shared content. What shall I do, Bogdan?
No, it's an error. Sorry.
Okay. Sorry.
Just go ahead.
Okay. So cool. So I was saying that dispersion relations were not altered at the low frequencies. Of course, this is easy to imagine because, for example, the mod shapes do not feel about the stiffness and mass changes at this very low frequency. Here, for example, we have the dispersion, let's say the mod shape animated in frequency terms for the for let's say this, yes, should be this one, this and these two modes that still are at the same frequency. Hierarchy also allows to the introduction, let's say that playing with the additional degree of freedom introduced by the hierarchy is possible to obtain some band shift. So basically we can see the green curve here shifting towards lower frequency, changing the hierarchical factor, and the deformation of the internal ring plays a key role in the let's say hierarchical induced band gap. Here I would like to bring your attention now on the second case, which is the dispersion diagrams of structures exhibiting hierarchy at different scale levels. The two scale levels here are the little cross highlighted in green and the big cross, which is the one highlighted in red. Also in this case, the let's say interesting thing is that we have the partial conservation of band gaps of the regular geometry. So here on the left, in the black, we have the dispersion curves for the little cross, so the green one, and we can see that we have a huge band gap, let's say a big band gap going from 300 up to almost 700. And then we have a second hierarchical level. In blue, this is a plethora of dispersion curves that if we zoom in, we can see that basically these curves are almost flat. This means that if we introduce in realistic model, which in realistic materials, that they always have a little degree of viscoelasticity, basically this will correspond to non-propagative modes. Here I would like also to bring your attention to one thing, to the fact that here in the very low frequency regime, where for the non-hierarchical structure we had the dispersion curves, so the material had the possibility to transmit the wave, here we have additional band gaps, this red. So the idea is this hierarchy allow us to open band gaps at lower frequencies, at the same time decreasing the structural weight. In this case, we calculated that it was around 45%. Also in this case, we have self-similarity of mode shapes. Here we can see, for example, the comparison between the first two modes, this one and this one, and this one and this one, that of course, due to the change of stiffness, they have been shifted towards lower frequencies. And here there should be the animation of the first one and of the second one. So let's say to understand why we had this band gap shift, we considered an equivalent mass spring model, which was capable to give us more insights about this type of materials. And in this case, for example, we, especially at low frequency, we consider the mass here as non-deforming structures, and the thin ligaments, springs connecting the masses. Of course, we can found the, let's say, band gap, low band gap bound as the root square of the rigidity divided by the mass. Theokaris said something. I didn't. Okay. So if
I've got a question for you, Marco.
Yes.
Regarding the spring mass model.
Yes.
Shouldn't it be some kind of asymptotic model based on beams, or why is it spring mass?
Well, we consider it be spring mass because if you see the deformation, especially at very low frequency, this big mass that I'm pointing here with the mouse, it simply, it doesn't deform. And so this is connected by this element here, which are connected by as the spring.
So you don't.
Of course. I mean, this is first approximation. Of course, I mean, you can start taking into account other more complex models.
So this doesn't allow for bending. This is just some kind of longitudinal or transformational motion. What is it exactly?
No, well, actually, if you give a look to the value k, which is the stiffness, it takes into account of both lambda and mu, so which are the first two Lamé constants. So it takes into account the bending.
Mm-hmm.
So if we introduce the hierarchy, we can see that basically we have a shift of this value of a factor of 3, which indeed is the mid-frequency gap in the hierarchical case. After this, we tried to experimentally, let's say, verifying that these calculations were somehow meaningful, and basically we performed a sample manufacturing by water jet cutting, starting from a unique pristine aluminum plate. So here the geometrical parameters are reported. And we can see that the hierarchical factor is again 20. So basically the small unit cell is 4 millimeter width, and the big unit cell, so this one, is 80 millimeter big. The nominal material properties are those of aluminium. And here is how the experiments have been performed. So basically we glued some piezoelectric transducers exciting the elastic waves in a specific portion, and on the other hand, on the other hand of the plate, we acquired the signal. Here, I just would like to bring your attention on this and this piezoelectric transducer, which basically corresponds to trying to excite in plane and out of plane vibration modes. Here, if we give a look to the comparison between the dispersion curves and the acquired signals, we can see that we have a good agreement both in terms of in-plane and out-of-plane polarized modes. This can be done by looking at these dispersion curves and knowing that the curves are color-coded. This means that, for example, the red curves, they mainly have a displacement that is out of plane, UZ, that is quite important. Whereas the blue curves, they are more living in the plane. And so you can see that here in gray, it is reported the in-plane bandgap, and with this light blue, it is reported the, let's say, complete bandgap. The same thing, so this was done for the low frequencies, and the same has been done for the high frequencies. Here, for example, we are at 340 kilohertz, and we can see that still we have a good agreement. The last thing that I would like to point out is if we give a look to the deformation, let's say, mechanism responsible for this wave filtering at different hierarchical scale levels, we can see that responsible for the low frequency Bragg bandgap is the big cross. So if we zoom here the deformation, we can see that half of the unit cell is deformed. While if we give a look to the high frequency excitation and we zoom in this area, we can see that basically already the first two rows of cross-like holes plays a very important role in reflecting the wave. So let's say that here, what I would like to bring you, the take-home message is that so far, I would say that hierarchy can be seen as a reproduction of the same physical mechanism at different scale levels. What I would like to say that if the cross-like hole structures exhibit a Bragg scattering bandgap, if we do it hierarchical, basically we will have the same mechanism of Bragg that will be repeated at different scale levels. The same it would be for locally resonance. So what I would say that in addition to these two mechanisms, which is the Bragg scattering and the local resonance, here is an example of like a waveguide. This is a plate with some pillar, and the idea here was to show that yes, the wavelength here is much longer than the unit cell size. So this was to give a little bit the idea of local resonance. But in addition to these two mechanisms, I would say that there is another bandgap mechanism, which is called inertial amplification. In this kind of mechanism, we have, let's say, three masses that are linked to each other by some spring, or elements that have a stiffness K and Ka, but they are not all aligned. So they have a angle theta, which basically is responsible for giving an increased effective mass to the system, which means that for small displacement U of the mass m, it will correspond a displacement that is much more important of the mass ma. So the idea here is very simple. So basically is actually, even looking at the nature, the hierarchy is not, the self-similarity is not perfectly repeated, but the idea is possible to use hierarchy as a leverage to introduce in the same structure multiple bandgap mechanism. So the idea, of course, is to relax the idea of perfect self-similarity to introduce other bandgap mechanism. Here is an example, for example, of already our cross-like holes that is becoming more and more full of holes, in which, for example, the connector here are replaced by an inertial amplification mechanism. Here we show the mechanism on how the hierarchy has been introduced. And here, for example, we start from the first level, which is this cross-like hole. Then we introduce these two still cross-like holes, but that are now stretched in such a way to properly fit in the mass region and in the connecting region. Then, of course, this will allow us to pass from the hierarchical level N1 to the hierarchical level N2. And once this is done, we can reproduce this kind of procedure for N hierarchical level. For example, here it is shown to pass from a hierarchical level N2 to a hierarchical level N3. So in this same cross-like structure, we reintroduce again this kind of design. What we found is that indeed this structure was able to reproduce multiple bandgap mechanism. For example, here there is the comparison between the dispersion diagram of the hierarchical elastic metamaterial of level N2. So this means this structure, and the inertial amplification structure. So basically this one, simple, without any geometrical changes. What we can see is that this design allows us to obtain a larger band gap, since we can have a shift, we can introduce a shift of this green mode that is highlighted here into lower, much lower frequencies. Another thing that I would like to stress on is the fact that also the attenuation performance is increased. Indeed, in this dispersion diagram, I've represented with the black dots the dispersion curves of the structures along the XM gamma X path for the hierarchical structure and along the gamma X path for the inertial amplification mechanism. But in violet, I have represented also the imaginary part of this structure. And the imaginary part basically tells us how fast the wave is attenuated. And we can see that here we have all a certain region of frequency values in which the attenuation values of these curves is much bigger than the other case. To better understand what is responsible for, let's say, this curve shift mechanism, we added some portion of the cross-like holes. So the CG is one portion of the structure, then another portion of the structure. And we can see that indeed is this sort of mechanism that indeed becomes more compliant that is responsible for this lowering of the red curve. If we go and we explore what is also happening at higher frequencies, let's say this one is the middle frequency range. So we go from roughly 1000 Hertz to 5000 Hertz. Here we can see that we have, again, a partial conservation of the band gap, even if a lot of rather localized modes came in. And we also can experience a slight band gap downshift towards lower frequencies. And we can see that some global deformation modes of the non-hierarchical systems are still preserved. This is the same, more or less the same things that happen for high frequency regime. The only things that we have to observe here is that being this small cross, the closing hierarchical level, the conservation of the band gap is total, apart from, let's say, these very flat bands here. And this is indeed due to the fact that this is the last hierarchical level. So the changes in terms of stiffness and mass modification are minimal. We also performed the experimental measurements of this structure on a finite sample, which is made of 3 × 3 unit cells. The structure was here excited by a shaker that is visible on the left top part of the picture. The orange wires here were suspension cables to suspend the structure in order to reproduce the free boundary conditions that were used for the simulations. And the frequency response function was acquired and averaged over the Chan points that are presented here. This is the in-plane view of this structure and also the finite element modeling. Also, in this case, we can see that we have a good agreement, I would say, between experiments and numerical calculation. So let's say that now we have seen that with the hierarchy we can do, I would say, some band manipulation, but the main weakness point and the major issue left open so far is the fact that by introducing in this, I would say, brutal way, the hierarchy, we have sensibly altered the stiffness and the mass of our system. So the problem is that we have to find a way to still have, still to address the great challenge of having lightweight structures, but with high stiffness. And so this is the problem that is known as decoupling, let's say, the stiffness and wave attenuation performances of phononic crystals or metamaterials. So in this context, we tried to lower a little bit down the level of band inspiration, and we went to the world of amino acids, which all except glycine are chiral. Just for those of you who are not familiar with the chirality, I would say that, let's say, in general, a molecule is called chiral if it cannot be superimposed on its mirror image by any combination of rotations or translations. This word chiral comes from ancient Greek and means hand, because indeed the hand is the first and easiest example of chiral structure. So basically we cannot translate or rotate our hands and superimposing one to the other. So this, let's say that the concept of chirality has been long known, especially in the world of photonic crystals, but recently has been introduced also in the world of elasticity, both from the static point of view and from the dynamic point of view. Here, for example, we can see examples of chiral systems that I called, that I called 2.5D, because indeed the structure is three-dimensional, but the propagation of the wave is still in the same plane of the structure. And here we can see a couple of examples in which, thanks to this chirality, we can achieve very nice and interesting properties, such as negative refraction, low frequency band gaps, and so on. So here I would like to present, let's say, how our chiral phononic system. The starting point is the one of a 1D translational oscillator. So basically a mass with a spring. This system can be modelized in 3D, like, for example, a disc connected with 3 ligaments, and is what you can see here. Of course, this system can, if we exclude bending modes, etc., it can translate only along the z-axis, this motion that is called U. However, if we add a twisting angle of these ligaments, we can see that we can have a kinematics that is more rich. And so instead of simply translating in the z direction, it can also rotate clockwise or counterclockwise, depending on, let's say, the nature of the angle that we give to the ligaments. Here, for example, it is reported a frequency response function of these resonators, both the translational and the translational rotational oscillator. Yes, here I would like to stress that the wave propagation and the structural rotation induced by the chirality are in orthogonal planes. But so now let's go back to the concept of bioinspiration. I would say that if we take, let's say, if we take this kind of structure and we simply stack one after the other, we could achieve what I would say, allow me to use this term, ordinary chiral phononic crystals. But if we give a look to indeed to how amino acids concatenate chiral centers to each other, we can see that the isotactic, or what I called here homogeneous, way of concatenating them is not the only one available. On the other hand, there is a very interesting, apart from the atactic one, which basically means that we take these chiral elements, these chiral centers, and we concatenate them in a random way. There is another one that is more, it's rather interesting, and is the syntactic concatenation, which means that we altern these chiral centers. So basically here we have R1, R2, R2, R1, 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 R2, R2. So this gave us the idea to take our structure, take our oscillator, translational oscillator, translational rotational oscillator, and do not simply start one after the other, but to have a mirror symmetry between it, and then produce a unit cell, which is represented here by this gray square, which the structure undergoes a mirror symmetry. So on the left, you can see the isotactic, what I have called before ordinary chiral structure. So here you can see that the rotation of the crystal of the ligaments is continuous. Here you can see that the rotation is inverted. So here we have a plane of symmetry. And if we give a look to the dispersion curves of this system, we can indeed see how the difference in the behavior is quite important. On the left side, we have the isotactic case. On the right part of the screen, we have the syntactic case. In the first one, you can see that we do not have any band gap, whereas in the second case, we can have a large band gap, highlighted also in this case by the gray rectangle, which produces from, let's say, rather 400 up to 2000 hertz. This is, the curves are also color coded. In this case, the color indicates, let's say, the twist of our disks. And what we can see that responsible for this totally radically different mechanism is the fact that while here we have the disks that they are all in phase, we can see that here the rotation of the top and bottom disk, they are out of phase, so white, black, which causes the central one to be still. So here, the thing that I've stressed before about all the properties that we achieved with the hierarchy were somehow had the problem of changing the stiffness of the structure at each hierarchical incrementation. Here, the idea of using this, let's say, the concept of tacticity to achieve the opening of bandgap where in other structure is not present is done at the same stiffness of the structure. So basically, to verify this, we put our specimens, both the syntactic and the isotactic, under compression tests. And here you can see that basically the reaction, the response for a 0.3 millimeter compression was basically the same. So these two structures that have exhibit radically different dynamic behavior, they have, on the other hand, the same stiffness. Just another thing, I would like to say another thing about this, and maybe the Professor Wegener will tell us much more during his seminar next week. One thing that one big difference that we observed between the two crystals was that, of course, in the syntactic, you cumulate the rotation of the disks, and so basically, if you encaster one disk, all the other, let's say, the rotation registered at each disk will somehow increase. Whereas if we have the syntactic arrangement, we have the opposition of phase that we have been discussed before. So basically, one out of two disks, we will have a condition of being still, and we will annulate the total twist of the structure. Here also, I would like to bring to your attention also that we manufactured the samples and we performed the experiments. The samples, you can see that are less than 10-11 centimeters long. Here, the structure reports 2-unit cell. Maybe in this representation, you will appreciate more the fact that this one is the isotactic. So you can see that the rotation angle is constant of the disks. On the other hand, here we have a mirror symmetry. So these ligaments go here, then it's mirror symmetried. And once again, here this is continuous. I would like just to, let's say, to conclude the talk with the last topic, in which another, let's say, will that since a long time has been in the mind of people working with phononic crystals, metamaterials, is once that we have these band gap properties, these negative refraction properties, nowadays even topological properties, etc. It would be nice that we could tune these properties at our will. So far, we have just seen totally passive structures. A room of work has been done about this, for example, conceiving periodic structures with adaptive elastic properties, which means that they were structures that they were able to tailor the dispersive diagram of a structure in a reversible way. These active systems, let's say, some of the work started with maybe, not started, but a very large area of research concerned piezoelectric materials, in which, for example, you can tune, you can couple a piezoelectric element to an aluminum bar, and basically when you feed this piezoelectric element with some specific RC circuit and you put him in resonance at specific frequencies, you can strongly alter the frequency, the stiffness of the structure, and you can even produce a passband. Here, for example, you can see this structure studied in the paper by Bergamini et al., in which you have a slab with some shunted piezos. If the piezos are not connected, you have a large band gap. Whereas if you alter the stiffness at your will, you can introduce a passband inside the structure. Other examples include temperature and magneto-based technique or actuated polymers and so on. For example, here I reported the case of a giant magnetostrictive material, which it was proved that under certain conditions, it can even go under 50% variation of the elastic constants. The last, but not maybe another, but not the last, is the application of an external mechanical load. And here, for example, you can see that into a phononic crystal, you can have, by stretching it or compressing uniformly in one direction or in another, you can achieve a band gap, let's say, shift towards higher or towards lower frequencies. So all these structures, they have anyway some complexity in practical implementation that may include the need for additional electric wirings, mechanical stability, physical contact requirements. And so here is where we try to look at nature again to see if there was the possibility to be somehow inspired. And here there are, I would like just to bring two examples. The first one is, let's say, it is well known that in nature there are materials that may change their shape according to environmental conditions. And here, plants, of course, is an example of this kind of evolving mechanism, which relies on internal heterogeneous architecture. And here is, for example, the example of a pine cones that close its scales when wet, and it and it open when it is dry. Another example is, for example, the one of sunflowers, which more than, let's say, more than phototropism, they are characterized by heliotropism. So basically, they have kind of sensor that is able to detect light and follow it. So the idea is here was to try to find somehow to obtain a similar behavior and have kind of photoresponsive elastic metamaterials. Oops. Oh, okay. So how to realize this? The idea is to introduce a light responsive elastic metamaterials by adding to a polymer a specific component, which is the bisphenol ethoxylate diallyl. Oh my God, we call it beta. I'm not a chemical engineering, so I cannot neither pronounce this. But anyway, the concept and the idea is to have a polymer, to dope it with a specific material that is sensitive to illumination of light at specific wavelength, so that it can change in a reversible manner its mechanical properties. Here, for example, there is our sample that we printed, which consisted of a slab with 8 pillars. The color of this specimen is red because indeed this BEDA is red. And the idea is to study how this structure that was printed by digital light processing 3D printing, how this structure could, in a reversible way, alter its mechanical properties and thus the dynamic response to a solicitation. In the experiments, we excited elastic waves with this piezo actuator that you can see on the right part of the structure. Then we illuminate selectively specific portion of our structure with a illuminating laser, and then with a scanning laser Doppler vibrometer, we perform scanning of the response, of the dynamic response of our structure. So let's say to start the first thing that we have done, we have calculated the spectral response of our specimen without illumination. So once again, we excite elastic waves here, and we acquired on the top part of each pillars that have been numbered from 1 to 8, and we can see from this figure, we can clearly see the let's say band gap nucleation mechanism. When we arrive to the 8th, the attenuation is the maximum, and it is in good agreement with the dispersion, numerical predicted dispersion curves, which is reported in this figure as the white dots. So the first thing, the first verification that we did, we verified the photo softening mechanism in a single pillar. Here we report a diagram that has the spectral weight, then we have the frequency, and we have the light intensity. And illuminating a single pillar, we can see that we have, as a general behavior, once that our structure is illuminating, a downshift of the frequency of resonance. As we said, this kind of behavior is introduced by, let's say, a kind of heterogeneous change of the elastic moduli within the pillar. And here you can see how the deformation mode of the pillar changes when the light is off, left part of the structure, and when the light is on, right part of the structure. As in the second step, we performed a scan to see what happens in time, but as a global response of the structure. And here, for example, we can see that despite we illuminate only one pillar, the global response is altered. What we can see is the transmission properties when the first pillar is illuminated with an intensity of 150 milliwatt as a function of time. So you can see that the illumination up to 100 seconds is turned off. So basically we can see that here we have a band gap in this very blue region here in transmission, which was exactly the same that we have been observing here. Then we, after 100 seconds, so we are at this point, this moment on, we started illuminating, then turning on the laser on the first pillar. If we wait a certain amount of time, that is, let's say, less than 1 minute, around 50 seconds, we can see that the band gap is enlarged. So here we have another region around between 60 and 70 kilohertz, that our transmission goes down. After 260 seconds, once again, we turn off the light to verify the reversibility of this process. And we can see that we recover, after, of course, again, these 50 seconds of time, we recovered the first part of the diagram, the first part of the transmission diagram, which corresponds to the original band gap. Here it's just a cut. I don't remember exactly when. I think at well, it's a cut between a time when the laser is off and when the time of the laser is on. And here we can see that indeed we have an enlargement of the band gap with the light. I think that this is the last or the last two slides. So just to verify that this phenomena was not something localized, we spatially resolved the spectral content of our structure. How we did it? So basically, in this case, we have on the left part, our specimen is not illuminated. So it's pure standard, let's say, standard phononic crystal. This diagram refers when we turn on the light, and here we have the excitation laser. In blue is the laser that produces the change in the mechanical properties. So the excitation laser is pointed onto the second pillar, always kept to the second pillar. And what is changed is basically the laser. This is the scanning laser with which we acquire the dynamic answer of the structure. And also in this case, we can clearly see that we can still achieve a totally different behavior when the light is on or when the light is off. this is the last trial of characterization, in which, on the other hand, what we have done is the opposite. So basically, we have been moving the laser responsible for the alteration of the mechanical properties. So the blue one, we have been moving it from pillar 1 up to pillar 8. If I have not been very clear before, the spot, the illumination spot, is corresponds to rather one pillar and a half. So it's quite limited in area. So we move the laser responsible for the changing of the mechanical properties, and we fix the scanning laser Doppler vibrometer at the end of our crystal. And once again, we can see that apart from the first pillar that where things do not change that much, starting from the second pillar and on, we experience a change of the delta frequency of the band gap up to a maximum registered of 38 kilohertz in the widest region, which corresponds to more than the double of our structure. I just conclude saying that this kind of behavior has been recursively, reversibly tried on more than 100 cycles, and there were no problem at all in repeating it. And it is also possible, it was also possible to tune its intensity, and so let's say determine how we would like to have the wave to be attenuated. Of course, this one is when the maximum amplitude was assigned to the laser illuminating the sample and responsible for the property changes. And this one instead was when only a fraction of the full power was assigned. The last thing I would like to stress on it is the time, because, for example, in literature, there are some other approaches based on thermal or other kind of contactless approaches. But in our case, the reaction time, let's say, is less than 1 minute. It's a matter of seconds, against several minutes, even 40 minutes in other cases. I just skip the conclusions because I think that, yes, I've been a little bit long. Before concluding, I just would like to acknowledge, let's say, the projects that allowed me to do this, all this kind of research and be in contact with a variety of scientists that allowed me to learn a lot. Especially, I would like to thank to Marie Curie and the current project Bohem that started basically this year. And I would like to thank two people in particular, which is Federico and Nicola, who were my first supervisor after my PhD, and who started believing in me and pushing me in writing European projects and so on. Then, of course, the group from Torino, led by Antonio Iozzi. Antonio, if you are there, sorry, because you are named Tommaso Del Pero, but you should be Antonio Iozzi. I apologize for this. With whom I have been discussing this photoresponsive research, and the EMPA group led by Andrea, with whom I've been working on this chiral stuff, and Chiara D'Araio, with whom also I collaborated in the framework of the hierarchical system. So thank you very much for your attention. Thank you again, the organizers, for organizing and making this event possible. And I mean, I hope you have enjoyed the presentation. Feel free to ask all type of questions, to start any kind of discussion, or to contact me for further information you may be interested.